Hocam burada prizin tutulması lazım sadece.
Ha?
Çalışmıyor.
Şunu mu çıkarmışlar? Evet. Ben çıkarıp öbür tarafa olacak. Dur bekleyin. Okay, so last time we started talking about using neural networks for the natural language processing tasks, and we started from a very simple example actually. We said that we are going to feed our words or documents or NLP related stuff to our networks, and they are going to make us some decisions. But at the beginning, we are going to start with very simple examples, and we started with this example, two-dimensional examples only, and that's what we are going to do actually. And we started talking about this last time, but I didn't go too far. Let's look at this example. We have a very simple example. Let's. Okay, this is good enough, I guess. Yeah, maybe I can just erase it. Let's define this problem. Okay. Let's say we have this very simple problem of giving advertisements to the newspaper about our, for example, car to sell. Let's say this is I'm trying to draw a figure here, okay. Let's say this is my car asking price, and this is how old my car is, car age, and this is the price. And let's see some example. For example, here, car price is very high, and my car is young. Okay, I think that this would sell quickly. It is high, it is high, but it is young, not very old car. How about this one? Would this sell? No, because it is both old and expensive. How about this one? Would this sell?
Yes.
Probably it will, right? And how about this one? That will definitely sell, right? Okay. But after some point, maybe this will not sell because it is too expensive. I mean, even if it is brand new, I don't want to buy such a car. So it looks like if I draw a line like that, that will separate the cars that is going to sell and the cars that won't sell, right? So the parts above it, maybe I should, the ones that are going to be sold, okay, not sold, maybe I'm going to make it like red, and the ones that would be sold would be like the green ones. Okay, so this is what I'm going to do. If somebody gives me a car number 1, I am going to represent this car number 1 with, okay, 2 years old, okay, 100,000 Turkish liras. Just two vectors, okay, a vector with two numbers, two-dimensional vectors, okay. And car number 2, maybe 5-year-old and 80,000 Turkish liras. So I'm going to represent my cars like that. And this will be my case. I am going to, these are my cars, or maybe I can call them x1 and x2. And I will multiply them with a weight matrix, okay? So this is x, and let's say this is x1, x2, this is w11, w12, w21, and w22. Okay, if I multiply this, I will get a number, let's say score 1, score 2. Okay, I am saying that find such four numbers, such four weights, so that they would produce appropriate scores when I give them these numbers. This score would be appropriate for a decision. That's what we are trying to do actually. Okay, so my features are xi and x1, x2, x3, etc. These are my vectors, like 2,000, 200, 5, 80, 10, 20, and etc. And my yi's are, they will sell or no sell. Okay, this will be sold in a week, or this won't be selling anytime soon. So it's going to be, this set is going to be something like this. Okay, so this one, 2-year-old and 100,000 Turkish liras. Probably this is going to sell very soon. Yes. Okay, this is one element. Okay, this is x0, y0, and maybe a 10-year-old car, and they are trying to sell it for 80,000 Turkish liras. This is going to be no, etc. Okay, so I have many of them. So where do I get these yeses and nos? I look at sahibidna.com, right? Okay, and if I see that a car is sold in a week, I just put those numbers somewhere, and I keep them for the whole year. So I have hundreds of them. So xi my inputs, and yi's are supposed to be my outputs. So the idea is, if I can learn such numbers, w1, w11, etc. For a newcomer car, a new car is coming, and I am asking the same question: can I sell this car? Can I assume that this car will be sold in a week? And I'm asking this question to this system. But I don't know these numbers. That's my task, is I am going to learn that number. So why am I giving you this example? I'm giving this example because this is a very simple problem, two-dimensional problem. I have just two numbers: how old the car is and how much I am asking for the car. Usually our problems are more dimensional. For example, for the sentiment analysis, I mean, given a sentence, you give me a sentence. Inside that sentence there are 10 words in it, and I'd like to know if sentence is a positive sentence or a negative sentence. I don't like this product at all. Okay, somebody gave me a review on my Twitter account, and I am a company, and somebody is telling me that the product you are selling is not good. Okay, is this a positive sentiment for me or negative sentiment for me? So this is a 10-word sentence, right? Each word, I can represent each word by 200 dimensional vectors, as we know. So it's going to be 10 times 200, 2000 dimensional vector for each sentence. So there's lots of dimensions, but the idea is going to be same. In that case, my W's will not be like 4 of them. It's going to be much larger, but the problem will stay the same. Only the dimensions will be high. And in 2 dimensions, I can visualize this kind of stuff much better. So my classes will be either sentiments, positive, negatives, named entities. We are going to buy sell decision, for example. Okay, sell this one or buy this one, etc. Okay, so let's look at them more carefully. That's what I said before. So this looks like my car price versus the car year graph, something like that. The sell or buy stuff. Again, this is a 2-dimensional stuff, and this one says that if I have such numbers, let me get rid of this stuff that I had written last week. Okay, if I had such numbers, those 4 numbers, I can come up with a probability calculation for that. Given the x, this is what I do. Okay, remember, x is a 2-dimensional vector. Wy is the row of the column y. Okay, I have only 2 rows because remember w is something like that. W11, W1, 2, 2, 1, and W2, 2. Okay, I am multiplying my x1, x2. So I am multiplying this row with this vector. That's what I am doing. So multiply this one with this one and multiply this one with this one. That makes the top part. Take the exponentiation of it, e to the power this number, okay, and that would give me a number, okay, a positive number definitely. Remember, this is the e to the power something, e to the power x graph. This is definitely positive all the time, whatever the value of x is. And in the denominator part, I do this for all the classes. I have 2 classes only, buy or not buy, okay, sell or not sell. Okay, I have 2 of them, and one of them has to be the y, okay, buy, sell not sell decision, or sell not sell observation. Okay, so this is definitely a number between 0 and why is this a number between 0 and 1? This is definitely, that doesn't matter what your x is. This is definitely between 0 and 1. It cannot be less than 0. Why? Because both of them are e to the power something. E to the power something is always positive. But I am saying that it cannot be larger than 1.0.
Didn't they sum it down for all C's?
Yeah, well, I mean,
So
this one is already included
right.
somewhere for some C value, right?
Right.
Right. That's why, I mean, it could be at most equal. In that case, it would be 1.0. Otherwise, it's going to be less than the denominator, the total of it. So it's like it behaves like a probability estimation. Okay. So it is up to us to find these 4 numbers for this case. Okay, for this simple case. How we find those 4 numbers? Well, I mean, calculating those 4 numbers, I need to go back and I need to look at this data that I collected from sahibinden.com. Okay, in sahibinden.com, I collected data from 100 cars, and I know their prices and I know how old they are. Okay, I know their prices and I know how old they are. And looking at those data, I can say that what would be my optimal W weight? Okay, what would be my optimal W weight? And from that I can decide, make new decisions on the new cars. Okay, let's go back and let's try to do that how we are doing it. So we looked at this one. Okay, so this is good. Okay, this is called Softmax Classifier. Okay, with the Softmax Classifier, you don't have to make a binary decision, sell, not sell. You can make decisions. You can make decisions. You can make decisions. Not binary decision, but more decision. For example, what you could say for a given word. Okay, let's say I gave you a word. What is this word inside this sentence? You could say that this is a verb, this is a noun, this is an adjective, and etc. Because this does not restrict the number of classes. Classes could be between 1 to C. Any number of classes is possible. So we like the softmax classifier a lot. The numbers are returned between always 0 and 1.0, and it can work for anything that we like. Remember about this multiplication. We said that this multiplication is a vector multiplication, right? It's just multiply this vector with this one. Okay, it gives you a single scalar number. That scalar number could be between anything between minus infinity to plus infinity. There is no restriction, but the exponentiation takes it to positive, and this one makes it between 0 and 1. Okay, good. So this one talks about the upper part. This one talks about the whole thing, and this one is called softmax. We talked about this. So we know, given those four numbers, given those W, okay, given the W, I know how to calculate this, but how am I going to calculate it with W? We are going to measure our compatibility with the training data. Given the training data, we say that if these are my W's, okay, this would be the training data performance. For that one, we measure this term named cross entropy. Okay, it looks a little bit complicated, but it is not actually. Okay, it is not actually. This is what we do. Let's try to do the same thing again. This is e to the power something. Okay, log is something like that, right? This is log. This is e to the power x. This is log x. Just the inverse of it, right? So this is what? Tell me again, what is this?
1.
This is 1 again, and this is 1. Right? Log, this is not log to the power x, sorry, log x.
Log x.
Or maybe ln x. Well, I mean, when I say log, it is, okay, it is ln, just the opposite of it. We know this, and this log, it looks like it doesn't work for the values that are. I mean, you don't take the logarithms of negative numbers. It is not defined, right? It is not defined, and between 0 and 1, it is all negative. After 1, it becomes positive. After a while, it grows very, very slowly. Okay, very, very slowly. So this one is what question? Okay, I'm not making these up. These are 200, 500 year old stuff. Okay, when I make this a negative, you realize how does it work when you make a negative? So it works like I'm trying to draw it with a green now. It's going to be like this, right? So this is the negative log. Okay, so that's what it says. This is called, okay, negative log likelihood of a softmax function here, log probability, negative log probability, and it comes from the actually information theory. Okay, you may remember information theory from some of your courses, maybe communication course or something like that. It says that you have a true probability, somehow you know it, okay, and you have a computed model probability, okay. So you know that the probability of that car being sold in a week, you know that probability somehow, and this Q is the probability that you are going to assign to it, okay? So you are trying to measure how compatible my model probability with the ground truth. This is how you measure it. This is how you measure it. Okay? This is how you measure it. And what you do is you, for all the classes from 1 to C, you multiply the true probability with the logarithm of the estimated probability and you sum them up. Okay? We like to use log here. I mean, it is not the reason why we are using log, but using log converts all the multiplications to additions. With the computers, adding small numbers is always better, right? With the computers, adding small numbers is always better. Okay, that's what we say all the time. Using small numbers, multiplying makes them very, very small, and there is an underflow of problems and etc. Log probability converts our objective function to sums, which is easy to work with, especially with the implementation with the computers. But the reason why we are using cross entropy is not that, but it certainly helps. Okay, let's look at this one. If I definitely know that for that class, okay, for that car, it's going to definitely sell, so it's going to be 1, and so for the true class, it's going to be 1. For the others, it's going to be 0. So this P will assign probabilities like this. Okay, just 1, 1. The rest of them are going to be 0, and that 1 will correspond to the correct class. And that means what? If I multiply this one with this one, this vector, I am going to get the logarithm of the computed model probability. Okay, so that's what it says. So remember, I am doing this for all the classes, and I am going to repeat this for all the samples that I have in my training set. Okay, because for each one I am going to repeat this calculation, and at the end I am going to get some large loss value. Okay, and it's going to be that one. So for all the samples from 1 to n, I am going to calculate this negative log likelihood of the softmax function, and this is going to be minimized so that I can obtain those x value, w values. Where are those w values in this formula? It is here. Okay, each fy is composed of this wy times x. Wy is just a single column of it, single column of those matrices. Okay. Any questions so far? Again, now I am talking about two-dimensional problem, but we are going to make it a lot larger in a few minutes. So what is the difference? Why I am minimizing this one, this loss function, but not this nice softmax function? Can somebody tell me? I am not minimizing the softmax function, but I am minimizing this loss function. Or, okay, softmax is here. Can anybody tell me? Or maybe before that.
Because it's negative log?
What that?
Is it because it's negative log, we're not trying to minimize it?
Well, negative log definitely helps, yet, but that's not the reason why we are minimizing this loss function. I'm trying to ask the difference between the loss function and the classification function. This one is a classification function. Okay, this one is a classification function. Given those w values, it calculates how likely I belong to that class. But this one is a loss function.
Does doesn't this evaluate like the entire model, how well it works or how bad it works?
That's right. Efendim? Buyurun. Aha, olur tabii. Aha, tabii ki. Hangi gün? Uygun. Hı -hı. Bir de bana e-mail atabilir misiniz bu konuda? Hiç hocam. Exactly what you said. I mean, this is trying to minimize the whole data set, okay? How about this data? What is included inside this data? Data includes all these W values, okay? So remember those 4 values? I am trying to optimize those 4 values so that this whole loss becomes a minimal value, okay? In optimization world, we like to minimize these kind of stuff. Maximization is the same thing, but minimization is a little bit more convenient. When you do the minimization, things kind of becomes more standard, okay? So we try to minimize this. That's why we have the negative at the beginning of it, okay? And we have the log because we don't have to multiply anything. Remember, these are the probabilities, okay? You multiply the probabilities. You say that I am going to calculate such a probability that giving the correct result becomes most probable, and that's the multiplication of the probabilities. But I am taking the log of them, and I keep adding them. Instead of multiplying them, I keep adding them. Okay, so that's what we are doing here. It's called loss function. So loss function and softmax is definitely related, but this is the one that we try to minimize to get our W values. Okay, so in a few minutes we are going to look at those, how we minimize those W values. Okay, and simple neural network does it with just a single matrix. Okay, softmax gives only this one. The problem with the single W, remember what we are doing, we get the W, this is our W is our matrix, 2 by 2 matrix. This is our feature vector or the sample vector. I multiply this, I get a vector, and I put it inside this softmax, and I get my result. But it turns out that I can only do linear stuff, so I can only say that above this line, I think that this car will sell. Below this line, I think that this car will not sell, etc. So this is very restricting, because whatever line I can draw, I can only get this much correct, because if I try to draw this line here to get, remember these green stuff, I cannot get them correct. If I draw it here, okay, now I am going to get these red dots wrong. Okay, that's not going to be good. So it looks like a line is not a good thing. Okay, for all the cases. Sometimes I want to use more complicated boundary models than the line. So maybe this one is better, right? Okay, so come up with a function other than my W times X stuff. Okay, come up with a better function than my line, so that I can get this stuff done. So for that one, we are going to use multi-layered neural networks, and it's going to be like that. Remember our W. Why do I keep writing? Okay, W. Okay, I multiplied it. Okay, I take this result. What does this give me? Okay, X is a vector, W is a matrix. This one give me a what? It gives me another vector, right? It gives me another vector. If I feed that vector to a function, nonlinear function, and that would give me another vector, and I would multiply with this now another weight matrix, and now I have nonlinearities. I can do stuff more than a line. I can do that kind of stuff. Okay, so that's what we are going to do in a few minutes. For that, we are modeling the human brain cells or mammalian cells, human brain cells. That's what we say we are doing. It is not exactly the same, but that's what we are doing. So these are the cells from the human brain or mammalian brains. This is the center of the cell, okay, nucleus, okay, and these are dendrites, and these are the terminal buttons. This guy kind of takes the inputs from the dendrites, okay, and it does some multiplication and addition, and it feeds that information to the terminal buttons, and these are all connected. Okay, these are all connected. This is a cell, another one, another one, another one. So far we did this much. So this one has 1, 2, 3, 4, 5, 6, 7 times 4. Okay, like 50 inputs or something, and some outputs here. Okay, see this output of this one. This is red. This is the output of this one is connected to the input of this one. Is connected to the input of this one. Okay, and each input is treated like a new information, and what are these connected? Where does the whole information? Where does the initial information come from?
From the senses, like eyes, fingers.
Yeah, exactly. From our touch sensors or the nose sensors or the eye sensors. So let's say I have a cell here that is sensitive to the light. When light hits this cell, this one sends some signal to this neuron. Okay, and another cell is here. This one is sensitive to sound waves. This one sends a signal to this one. So this one is calculating dumb stuff and making this calculation to that one and that one and that one. It goes that way. So they have observed this kind of behavior in 1950s, okay, through some experiments, and they say that why don't we use the same idea for the computer neural networks, and that's what we are doing for the last 50, 70 years. Okay. So that's how they model the neurons. They say that it has inputs, x1, x2, and x3. This is our neuron, and this is the output. Okay. So for each neuron, I have this input, x. I multiply it with a matrix like that, okay, and I add a bias vector to it, and the overall result will give me a number like that one. Okay, so multiply x1 with one of the elements of it, x2, x3, and do this thing too, and at the end pass it through this function, this activation function. Let's look at this function actually. This is called sigmoid. And this sigmoid can behave like a, remember softmax? Softmax gives us a number between 0 and 1 for a number of classes. This one behaves like that, but it behaves only for a single class, okay? This one returns a number between 0 and 1, okay? That's why it's called logistic regression. What is regression? What is regression? Do you know what regression is? If you listen to class, maybe you will. So tell me what regression is. You should know it. You know it. What is regression? I am sure you heard about it. What is regression? What is classification? Classification? What is a class? In a few minutes ago, I gave you an example about the car selling or not selling. Each one is a class, right? So it's a classification problem. But if I ask what is my age to a computer system, it doesn't tell me 1, 2, 3, 4. It says your age is 2.71 years or something like that. Okay, that becomes a regression. So regression produces a continuous value. Classes produce what? Classes produce discrete values. Okay. So for the sentiments, when I say, is this tweet a good tweet or bad tweet? Okay, or positive or negative, I would get positive or negative. Okay, positive or negative, just one discrete value. But if I ask a question about, given the picture, photograph of a person, what do you think the height of this person is? It doesn't give me a discrete value. It gives me a continuous value. That's called the regression. This one sometimes is called logistic regression. Logical value. What are the logical values? Logic values 0 and 1. This one produces a value between 0 and 1. So if it is closer to 0, we say that it is 0. It is closer to 1, we say it is 1. So it could be anything in between. Anything in between. And let's see how it works. Let's draw this. Okay, that's the formula. This is, okay, this is, I am going to draw it. This is e to the x is like that. Okay, this is e to the x, right? It doesn't become negative. E to the x, e to the z maybe. Okay, e to the z. What is e to the minus z? How do you write e to the minus z? It becomes like this, I guess, right? Something like this. That was bad. Can I do it? Yeah. This is e to the minus z. How do you calculate this one then? 1 plus e to the minus z. 1 over 1 plus e to the minus z. When this is very large, this becomes 1 to the large value, it becomes 0. Right? So this one is going to be 0 here for very small and very large values. Is that correct? For very small values, okay, this one is going to be very, very large. So 1 plus large value, 1 over large value is going to be 0. How about z is very big? When z is very, very big, this one is going to be 0, so 1 over 0. So it's going to be exactly like this, like the blue line. Okay? So whatever value you give it to, okay, it's going to produce a value between 0 and 1, and it is nicely differentiable, and it's nice. So I can use this function as a simplified softmax function. Okay? I can use it as a simplified softmax function, and that simplified softmax function is going to be useful. But most of the time, since our things are not binary, we have many classes. Instead of using this, we are going to use softmax functions. Okay? So again, this is called logistic regression or sigmoid function, and they are related to softmax function. We don't use these kind of structures by itself. We do it this way. Okay. So we feed information, 1, 2, 3 things, and each one is doing their calculation and feeding it through this F, and it is producing. So I gave 3 numbers to it. It produced another 3 numbers. That means what? That means I can put another node here, and so it would produce another value between 0 and 1. So
What's the
it
plus
looks like
1 at the bottom?
what?
What's the plus 1 at the bottom?
It's for the bias. It's for the bias.
Isn't the bias usually on the edges themselves?
For each node, there is a bias. It is because suppose all of them are 0. When all of them are 0, all that multiplication and addition will produce only 0. Okay? So you should learn something when the case all the inputs are 0. That would be the number bias. Okay? So in that case, what's going to be your value is going to be this much. Okay? So I added this, and I have this one right now. Okay? I can keep adding this more and more. I have many layers. And human brain works this way. So each one, okay, in this case, remember in this case, this is one layer, and this is the second layer. Okay, 2-layer network here. Okay, I have, okay, 1 layer, 2 layer, 3-layer network here. Okay, so deep learning means that you have many layers of it, more than 10 layers. Nowadays, they are doing more than 100 layers with the deep learning networks. And if you can train it, if you can determine those numbers, okay, those numbers for each of the nodes, then that means that we are going to be successful in learning this kind of stuff. Google has a very nice, maybe some of you know it, neural network playground website. You can say that kind of stuff. Okay, so I have 2 inputs, x1 and x2. Okay, and it looks like, okay, okay, good. This is one good. This one is good. Okay, I will. Okay, so somebody gave me this, again, 2-dimensional. Let's say this dimension is the car's age, and this dimension is car's value, price, and I am trying to find a boundary between these two, so that for any given value I can do this. And I am asking this tool, okay, find me good values for x1 and x2, and this is what's happening. Okay, it says that in a few minutes I am going to give you, and your values will be 0.88 and 0.75, just 2 numbers. Okay, so which is very nice. But in this case, the problem is very convenient. The problem is so nice. I can find it. How about this one? Okay, in this case, all the positives are in center and all the negatives are outside of it. 2-class problem. If I ask the system to find those numbers for me, it cannot do anything. It says that my loss is 0.5, my training loss is 0.5. Doesn't work. It doesn't go to 0. In the previous one, loss was immediately 0. I minimize it very nicely. See, I minimize it very nicely. Loss is 0.001. Even if I do For example, if I add noise, what is noise? Noise is like that, okay? So as you see, my data is a lot noisy now. Positives and negatives are intermixed. I am asking to optimize this from the Google Playground. Well, it is not, it is doing a good job, but noise is not, the loss is not going to be 0.000 because my data set is noisy. Okay, my data set is noisy. I cannot do more than that. And if I increase the noise amount even further, like that, okay, it's going to be 0.1 test loss. There is no way that I can get 0.00 loss value on this one, because whatever you do with a line, you cannot do better than that. Okay, but these kind of cases will be okay. How about this one? Can I do that? Can I optimize it? No, again, loss is not going anywhere because line is not going to separate it. For that, I will add hidden layers. Okay, so I can specify now more than a line. I can do better than that, and I am asking Google Playground to optimize it to do for me. As you see, loss is getting smaller and smaller. It looks like my loss is very small now, right? So it found this boundary for me. Previously, I couldn't find this boundary because previously all I can do was a single line. A single line is not going to do for this case. And it looks like a hidden layer, okay, one more layer, okay, 1, 2, 3, 4 nodes, and then a single node at the end was going to be the answer for now. Okay, activation function. Each of these has their own sigmoid functions. And how about this one? This one has 2 inputs. 1, 2. How about this blue one? How about that blue one here? 1, 2. It looks like it has 3 inputs. What is that blue line? Blue one? Well, I'll say bias. So, Usama, this is your answer. That's the bias for each node. So it has 1, 2, and 3. Okay. So play with this one. Add more layers. Some of them are difficult to do. For example, this one. See? It's like a spiral. It is difficult to separate this one from each other. So it is going to do some good attempts on it, but it looks like it's kind of stuck. Maybe even 2 layers are not, a single layer is not enough. Maybe I should add 1 more layer with 2 more stuff. Now do it again. Sometimes you will need to wait more because I didn't tell you about the optimization algorithm, but in a few minutes we are going to talk about it.
But
It's not, yeah. Well, it's not too linear. It's not linear because I know that it can separate a circle from the concentric circles. This one is not doing very well. Add more layers, play with some other stuff. By the way, you can treat this as a classification problem or a regression problem. Okay, so see, this is a regression problem. You don't have 2 colors anymore. Very dark blues, very dark yellows, and in between. Okay, but I was running the classification problem. Anyway, play with this tool. It is a nice tool to learn about, experiment with the neural networks. And deep learning doesn't mean anything more than deep neural networks repeated many times. Okay, good. Any questions so far? Okay, so if there are no questions, let's take 10 minutes of break. Okay, where am I here? Okay, so let's be here around 14:35, and while we are out, let's open the windows.
Bunları yarım açsak da burada çünkü düşüşen şeyler olacak.
Senin kimden mi? Ha ya, nasıl gidiyor?
Öyle gidiyor.
Ha, senin de bu konulara benzer mi?
Yok ya, alakası yok abi. Eğer yapıyorum.
Her şey görüntü işlemi. Ha. Yani arada bu tür şeyler kullanmıyoruz değil mi? Şeyde de var biraz da. Mesela şimdi hoca, Erhan Hoca biliyorsun orada görüntü işlemeler söylüyor da onun da şeyleri,
Yani
bitirmeler burada bunlar var biraz.
var mı?
Var var. Bunlar.
Ya benimkinin pek onunla alakası yok. Ben hazır teknoloji
Hazır derken nasıl bir şey?
Unity kullanıyorum.
Ne bu? Ha, Unity ya.
Bir şey kullanıyorum.
Unity'nin öyle araçları var mı?
Yani
Görüntü
Tutorial
işleme.
diye bir şey var. Unity'de kullanabiliyorsun. AI teknolojisi. Onu yapıyorum.
Peki o şeyde dersini alıyor musun sen ya hocam? Onda çok temiz, ikisi öyle
Ama
ama.
yani o derste de çok bir şey görmüyoruz ki yani.
Yani
Anlamadım. O ders birazcık şey oldu. Anlamsız oldu.
Anladım yani şey. Muhtemelen teknik kalır böyle.
Yani o teknik kalıyor birazcık.
Evet, anladım.
Sen ne yapıyorsun?
Ben Erdoğan hocam ve mobil uygulama artı işte şey var benim. Sentimentalist var. Şimdi onu işte birleştirme de biraz sonuçta pek iyi değil yani. Şey güzel oldu birleştirmesi. Yani basit bir model ektir. Python Flask kullanarak da API yarattım abi. Bağladı oradan sunacağım değil mi? Ama orası güzel oldu işte o model biraz dandik yani. Çünkü şöyle dandik.
Zamanın gelişiyor herhalde.
İşte hoca ödev verirse belki oradan yırtarız. Yani o ödevi yaparım.
2 tane şey verecek misin?
İşte aynen birini sentimetre verirse onu ona yaparım çünkü şey kolay. Modeli eğitiyorsun ya kanka. Doğduğun üstü diye modeli export ediyorsun. Kullanıyorsun.
O kadar.
Aynen.
Yani bayağı iyiymiş bu.
Dataset konusunu bulamadım. İngilizce buldum o yüzden cümle İngilizce, Türkçeden İngilizceye falan çeviriyorum. O biraz dağıtıyor falan. Ya şöyle, Python kütüphanesi var normalde web sitelerine tabi. Yorum yapıyor. O tür şeylere girince kanka biraz zaten mobil uygulama.
İşte onunla uğraşacağız.
Yani 5000 satırdan model kod yazmış. Yani. Ama mobil bir şey de. Gayet etkili bir şey var. Tüm butonun sağa sola gitmesini kod ediyoruz.
Çokmuş ama. Sırf yürü için bu.
Dünya yaptı, sen dünya yaptı, tutarayı falan sonra. Benim adam butonun butonun kod ediyoruz.
Anlaşılır bir falan yok mu?
JavaScript olmuş. Yalnız seçebilir ne oldu? Birinci değil.
Ona kolay olur bu oyuncu.
Evet.
Okay, so since we have more than one layers right now, maybe we can talk about the layers like a single unit. So this is what we do. For this neuron, I multiply, okay, for this neuron, I multiply my inputs, these three numbers plus the bias, with these four numbers, W11, W12, W13, and B1, okay? And for this one, I am multiplying with these four numbers, and for this one, there will be four different numbers. It looks like I have a matrix like this. I have a matrix like this, and it is W11, W12, W13, and B1, W21, W22, W23, B2, and etc. B3. And this one will be multiplied by my x1, x2, x3, and 1. Okay, so I have this matrix here. All these numbers are formed into a matrix notation, and I multiply it with this input, and I would get three numbers out of it. So this is a matrix times a vector. It's going to produce a vector, okay, and it would produce another three numbers, and I can repeat this process over and over again, depending on my decision on the number of layers, okay. And before I this is the notation, wx plus b. So it looks like this guy didn't do it the way I want. Okay, said that maybe just do this. Take these three out here, put it in. Nope. Put it in here, and take these. Like that, multiply these three with this three, and then add this one here. Okay, that's what they did. Okay, but before this, and this is called Z. Before I propagate my Z to the next layer, I pass it through this activation function, which is sigmoid in my case, and those activation functions are different. They change from time to time, but it looks like this one is sigmoid. And what kind of other activation functions I have? Hyperbolic tangent, okay. This hyperbolic tangent changes from -1 to 1, and this ReLU changes from 0 to infinity. It's very simple, and linear is just a linear, just to experiment with those. But for now, we are going to look at just the sigmoid. That's the classical one. Okay, so again, this means, I mean, this is not a function that takes a single number, it's a vector. So you keep applying this function to each element of this vector. So the output is a three-dimensional vector out of that. Okay, good. So that nonlinear, so the thing is that if I don't define a nonlinear function here, doesn't matter how many layers you have, you're going to end up with a nonlinear relationship. That's not going to be good. So this is going to be a nonlinear function, and I'm not going to talk much about it. So let's go back to our original problem of natural language processing and named entity recognition. That's what we are going to do right now with this new technique of machine learning and neural networks. Named entity recognition, I think I talked about this before, is trying to find and classify names in the text. For example, the European Commission said on Thursday it disagreed with German advice. So in this sentence, the names are here. The European Commission is a name, it's an organization name. Okay, German is another name, it's miscellaneous. I'm not going to give a class. Here, France is a location, Britain is a location, Fischler is a person, etc. So I have how many groups, how many classes? I have organization, person, location. I don't have an example here, but there is a time, okay, time there too, and miscellaneous. Okay. So 1, 2, 3, 4, 5 classes, and the rest of them are classified as others. Okay, 6 classes. So for each word, I need to assign one of these classes. Okay, for each word, I need to assign one of these classes, and that's what my task is, an NLP task. And this will be very useful for these kind of purposes: tracking mentions of particular entities in documents. Okay, give me information about, for example, give me information about Turkey news. When you say that, okay, you need to find the keyword Turkey in all the news articles, but that Turkey should not be the bird Turkey, right? It should be country Turkey and etc. Okay, again, for the question answering, remember when you ask, okay, what is the capital city of Netherlands, for example, when you ask this question to Google or something like that, okay, you need to find a sentence somewhere on the web that talks about Netherlands as a country, and that talks about the city of the capital city of Netherlands as like a location. And it is important to do that kind of classification. And the nice thing is that I don't have to parse anything to achieve these classification. I don't have to do morphological analysis most of the time. I can do it in a straightforward way, given a data set of already marked words. I can keep doing this. So how am I going to do this? Okay, this is one example. Foreign Ministry spokesman Shen Gaofan told Reuters that, etc., etc. So, organization, foreign ministry, person, okay. This O means other, Reuters, okay. So I am going to, by the way, this organization, this is not a separate organization keyword, okay. This is the beginning of organization continues. Beginning of the person continues, and etc. Okay. So that's how they do it. So why do you think that this is the NLP problem? Where is the ambiguity? Ambiguity is here. For example, First National Bank donates 2 vans to Future School of Forsyth. Okay. So you understand, as human beings, it is easy for us to understand that there is a bank. Its name is. What do you think? Is the First National Bank the name of the bank, or the National Bank is the first bank to donate?
National Bank. Not the first one.
So it requires some real world knowledge, right? It requires some real world knowledge. Since we don't live in USA, we don't know that there is a First National Bank or National Bank. Its name is First National Bank. Okay. First National Bank is the name of the organization. So it is harder. Should I make it a national bank or First National Bank? Hard to know if something is an entity, okay? For example, to Future School, is that Future School is the name of the school, or School of the Future? We don't know, okay? We don't. For example, this name. If you are not familiar with if you are not familiar with the things that people talk about in USA, we wouldn't know if this is a person name or some kind of a phrase, some kind of a place name, or we don't know. Okay, so what are we gonna do? Well, you need to look up somewhere. So it is not a very easy. For example, this Charles Schwab, you know what Charles Schwab is? It's a financial organization. I think they do some investing, that kind of stuff. And but if you have this sentence where Larry Ellison and Charles Schwab is a person actually. he founded this company named Charles Schwab. So his name and the company name is the same, but I think this guy is dead now, a long time ago. So when you say Charles Schwab, it usually means an organization, not a person. So, I mean, at the end, all in all, this is not an easy problem. Typical ambiguous NLP problem or artificial intelligence problem. Okay, so what are we gonna do? This is our first initial approach. Word window classification. Okay, idea is classify a word in its context window. So what am I gonna take? I will take 5 words or 6 words or 7 words, and I'm going to assign a class, named entity class, to the center word. Okay, so it's going to be either person, location, or organization. Okay, so that's what's going to be in our case. Okay, simple way to classify a word in context might be average the word vectors in a window, classify the average word. Okay, you could do that. Okay, let's say this one says that if I have 5 words, just add them together, all the word vectors, and take the average, but that would lose the position information. Better thing would be like this. Okay, museums in Paris are amazing. So I am going to assign a class for the center word Paris. Okay, and Paris could be a person, Paris could be a location, Paris could be, for example, a company name. We don't know, but in this context, it looks like Paris is a location, right? So it's a location. So that's why the context is important. So that's what I'm going to do. I will get the word vectors for each of them, put them together, and I'm going to make a new X vector. Okay, its size will be 5 times D. D is the regular. D is the regular word vector size, right? And that will be the input to my whole network. And when the whole network runs, at the end of it, I will run a softmax function, and softmax function will give me the probability of each class for this center word expires. Okay, that's what the plan is. Okay, that's what's going to be. Okay, we already know these for our softmax classifier, and this is the one that we are going to minimize. Remember that Google thing, Google Playground, it was trying to minimize a loss, and that was a loss. Okay, good. We are going to come back to this one later, and we already said that we are going to do the multi-layer perceptron. That is, we are going to run these one after the other, right? That's called multi-layer perceptron. Okay, and that will be our decision now. Okay. So at the input layer, I have what? How many? Okay, I have 20-dimensional vector. Well, we simplified the problem a lot. Normally, for each word, we have 200-dimensional or 100-dimensional vectors. I am just using 4-dimensional vector for each word. I simplified it for the sake of putting everything together in a single slide. Okay, so X is my input. The size of X is 20 by 1, so it is a vector. It is 20. So I multiply this X with a weight matrix of 8 by 20. Okay, why 8? Because I have 8 nodes or 8 perceptrons in my hidden layer, and the output is going to be 8 times 2. Why? Because there are 8 inputs, and I will have either it's a Paris is a city or not. Okay, just two examples, two classes. Okay, so that's the whole thing. Multiply x by this w. So when you look at this one, that's the whole calculation. Okay, given the x, I will get these scores. What are the things that we don't know in this equation set? What are the things that we don't know in this equation set? X we already know because that's the input. W and B, and the results are calculated, are they fed through this F. F we already know it is the sigmoid, right? And then we have, I know A because it is here, and U. Okay. So the things that I don't know are these 160 numbers and 16 numbers here. Okay. I lost that part of the class altogether. You guys are not listening at all, right? Are you watching my video on those cell phones? That's what I guessed. Yeah, thank you. I am saying the same things here too. Okay. So all these numbers have to be calculated somehow by looking at our data training data. That's what we are doing. Okay. So it has a very big advantage to have this kind of input, because if the context is right, then I would say that Paris is a location. What does it say? Only if museums is the first vector, should it matter that in is the second position. Okay, so we can make these kind of, I mean, the network can make these kind of decisions in the end. Okay, so before going any further, let's look at how we optimize stuff. Let's say I have a function. Let's say I have a function like this, very simple function, and I like to minimize. Obviously, this is a one-dimensional function. This is a one-dimensional function fx. This fx has a minimum here. I can see that, but numerically, how should I find the minimum of this function? Usually, I do this. I start. What's that?
Take an integral of it.
Take the derivative of it, but usually these kind of functions, taking the direct derivative is not. Take a derivative and equal to 0 and solve it. Okay? I mean, this function is very simple function. I can take the derivative for equal to 0. But for some cases, for example, for single dimensional, for 1000-dimensional problems, taking the derivative and equating it to 0 and finding the solution is not that easy. Even if you did, you will not find the correct result. So numerically, we try to find it. This is what we do. Let's say I start from this position. I'm just trying to guess. I said that this is my minimum position. Okay, this is my minimum position. Let's say this is x1. Okay, fx1 is here. Okay, at that position, I take the derivative of f at that position. Okay, taking the derivative at a given position is easy using some numerical technique. And derivative means what? Derivative means that it's going to give me this slope, right? Okay, this tangent line. This tangent line is telling me that at that position, the function f is decreasing, right? To the right. What is the slope? This is a negative slope, right? So it's going to be, maybe I should do this. Maybe I should take x1, okay, and subtract some number derivative of x1 multiplied with this alpha. So I mean, why is it minus? Because I mean, you want to go towards the negative side of the slope because you don't want to increase it. Otherwise, I would go upwards to the left. I don't want to do that. So what is this alpha? Alpha is my step. I like to go this much. If alpha is too much, I would move too much to the right. So I moved a little bit with this number. Now I have x2. x2 is here. Okay, and this is fx2. Okay, and I take the derivative of it. Now it's again the derivative, but it is kind of its slope is better. It is not that as steep, but I am going to keep doing this. And let's say I moved a little bit, but I overshoot, and I got this x3. Okay, so when I do this x2 minus derivative of x2, I got x3 now. Okay, now x3 says that my slope is going to be that way. Okay, so eventually I will find this location which will produce me a derivative of 0, and derivative of 0 is going to be a line like that. So I found it. But you might say that, I mean, your initial suggestion, why didn't we take the derivative of an equate to 0 and solve it? Well, I mean, for one-dimensional problems, it is okay. We can do that, but for many-dimensional stuff, it is not that easy. And the other thing is that if my function is like this, okay? So this one has 1, 2, 3, 4, 5, 6 local minima, 1, 2, 3, 4, 5, 6, 8 local maxima, and if it's a periodic function like cosine and sine, there are infinitely many solutions to it. So it is not that easy even for a single dimensional problem, and we are going to do it for sometimes million dimensional problems. That's what we are going to do, because in our case our problem is going to be 160 plus 16 is going to be 186 dimensional, 76 dimensional problem. That's what we are going to do, and we are going to follow this rule. Okay, get the number, okay, the initial position, move it along the direction, negative direction of the derivative of that function with this step alpha. Okay, that step alpha depends on you. You choose it. If this step alpha is large, your steps will be larger, and sometimes you are going to miss this minimum. If it is very small, it's going to be very, very slow. That's not going to be good. And this is how it is visualized on a single dimensional space, and this is how it is going to be visualized on multi-dimensional or two-dimensional. Where did it go? Yeah, it is. Let me visit it. I'll try to make it bigger. Where is my nice figure? Is it okay? Here it is. Okay, it looks like this guy has started at this point. Okay, this is a fxy equals z, right? Z equals fxy, two-dimensional problem. I started at this point, and I follow the gradient. Maybe I stop here, then there, and I change direction, and I found this minimum. Okay. I was lucky in this case because there was a path to the minimum. It was a nice function. Most of the time we are not that lucky. Sometimes you can't find the global minimum by doing this numerical method, but we can't do better than that for very high dimensional problems.
I mean, it interestingly curved at the right side.
Well, they designed it to look nice, right? Yeah, they designed it very look nice. In fact, I think there is a local minimum there too, but anyway, so Just play along, okay? So that's what we are going to do, okay? That's what we are going to do. We are going to do gradient descent to find those optimal numbers. Okay, so that's called the stochastic gradient. Let's forget about this stochastic stuff. We are going to do this gradient descent. In our case, our theta includes 176 dimensional vector. Our old theta, okay, we will evaluate our loss function at that theta, and we will take the derivative of it, multiply it with some alpha, and subtract it and move it that way. Okay, let's look at this in more detail. If there are no questions, okay. No, I opened the wrong viewer. Okay, I have stolen these slides from Manning, okay, a very famous NLP researcher at Stanford, and I think this is his first or second year of teaching NLP using the neural network, maybe. I don't know, and there are some errors in the slides and etc. But so this is what we are doing, okay. Binary classification for center word being a location. Okay, we are trying to produce a location, and our 20 dimensional input, and then here I have a W, which is a 20 by 8 by 20, and our 8 nodes, and we have this single node here. It will take all that information, and at the end I have a logistic regression. This one will produce a number between 0 and 1. If it is 0, it means it is not a location. If it is 1, it is closer to 1, it is a location. That's what we are going to do. Okay, and we are going to do this gradient descent again. Forget about the stochastic for a while. Okay, let's talk about this gradient descent. First, okay, I will follow these slides. It's going to give us some nice review of the derivatives and everything. Everybody knows this, I hope. If a single dimensional function x3, what is the derivative of this x3 with respect to x? This one, okay, you know how to prove it using the definition of the derivative and the limits, and we are not going to talk about it. So no problem for that one. But we are not dealing with single dimensional functions anymore, okay? We are dealing with these kind of functions, okay? We have n dimensional functions. Our functions are going to be 160 dimensional functions, etc. How do you take the derivative of it? Okay, well, this one doesn't depend on a single x. It depends on a number of things, so we take the partial derivatives. Okay, if you take the derivative of such a function, you don't take a single derivative, you take the n dimensional derivative. So derivative of such a function is n dimensional vector. We already know that too. Okay, so we never did that, but it's going to be. So what does that say actually? If I take the derivative of this function at that point, it's going to give me a two-dimensional vector back, and that two-dimensional vector is going to be the direction that the opposite of that direction is going to be the direction that I am going to follow, because I am moving into a two-dimensional space. Okay, so that's the gradient. So, well, these functions are closer to what we are trying to use, but ours is even more complicated. We are going to talk about functions of functions. Okay, this function has one output and n inputs. This one. How about my function has n inputs and m outputs? Okay, n inputs and m outputs. It's like it's like this. It's like remember the other. Can I show you that? Remember our each layer takes n inputs and m outputs, right? Depending on the number of nodes. That's what's going to be, okay? So what am I going to do now? Well, I will keep taking the derivative with respect to, okay? I am going to take the derivative of f1 with respect to x1, x2, x3, xn, and keep doing this until I had fm. Basically, what you have is like m functions working on n inputs. Each one is a node. Each one is a perceptron. Okay? So this is, by standard definition, is called Jacobian matrix. Okay?
And each of these functions is just to calculate the next perceptron.
That's what we are going to use it for, but this is a general definition. Jacobian matrix is not invented for our neural networks. It's just a standard calculus definition. And we are going to use it, as you said, we are going to use it to calculate the derivatives for each of those neurons, yes. Okay? So, I mean, maybe you have never, definitely you have seen this, I hope, from high school. And this one, you have seen it, and you have maybe you didn't see it, but just a generalization of the derivative of the functions, okay? So if you have a function with n inputs and n outputs, so this is the stuff. First row is the derivatives of the partial derivatives of the first function, second function, and function number m. Okay? Okay, let me move on then. You remember the chain rule. Z is equal to 3y, but y depends on x, and y is equal to x squared. So we are going to take the derivative of z with respect to x. So how do you do that? The chain rule says that take the derivative of z with respect to y and take the derivative of y with respect to x. Is called the chain rule. And okay, how about dz over dy? It is 3. dy over dx, it is 2x. It is 6x. So that's the chain rule. Okay, we kept doing that kind of stuff. We gave our input to a matrix and multiplied with matrix and add this one. The biases, I get another vector. I give this vector to f and I get this h. So it is very similar. So I can apply the chain rule to this case. Take the derivative of h with respect to x. Okay, x's are important. Okay, how am I changing? And later I'm going to change. I'm going to take the derivative of h with respect to w. Okay, so. Let's do that actually. Let's try to do that, okay?
So the H is the next place we are going to, or?
H is this. H is, remember this one? So x is our input, 20-dimensional vector. W is our 8 by 20. B is what? B is an 8-dimensional vector. Okay.
H is the next layer.
Yeah, and we are feeding this h. H is a vector, really. Yeah, we are feeding this h to the next layer, and later it's going to be multiplied by this u. U is another matrix. So we are trying to figure this thing out. Okay. So. What is the, okay, again, chain rule says that take the derivative of h with respect to z and take the derivative of z with respect to x. That's what we are going to do, okay? So take the derivative of h with respect to z. Remember, z is just a vector, right? So each one has its own stuff, okay? and H is a vector too. So it is like many inputs and many outputs. We are going to do the Jacobian thing, okay? We are going to do the Jacobian thing, but in this case, I know that only the Zi's depend on the relevant ones, and in this case, it's going to turn out to be like that, okay? So I get a new matrix. In that matrix, all I am saying is that I am taking the derivative of f if I and j are the same in this case, okay? I and j are the same. Otherwise, it is 0 because they don't depend on the others. So we are going to get one nice diagonal matrix out of that Jacobian. You might say that, why didn't we get the same effect when you are doing this definition? In that case, I didn't know what kind of functions f's and x's we have. Okay, this is the most generic way of taking the Jacobian. In this case, I know it. It is diagonal. Okay, it's a diagonal. Okay, so I took this one, and I can continue, and later I can take the second part too, which is this one, x with respect to x, but taking the derivative of this one with respect to x is going to give me this w, and I know that one. Okay, so there are a few others. For example, this one. Okay. I mean, if you do the math, you are going to get this. X is a vector, W is a matrix, B is a vector. Okay. If you take the derivative of this whole thing with respect to x vector, you are going to get this matrix. This is really interesting, right? I mean, at least interesting to me. It looks like regular calculus, but you are doing this with vectors and matrices. Okay, so notation is very nice. I can talk about matrices and vectors, and I can do that kind of stuff. And another one is this one. If I take this derivative with respect to B biases, there is nothing about the biases inside this W or X, but it is here. So I will get the identity matrix back. Okay, it's going to be an identity matrix back, and that's it. What else? And third one is this one. This kind of makes sense. Well, I mean, what is this? This is a vector and this is a vector. Vector and vector. If you transpose one vector and multiply with the other one, you are going to get a scalar back. But if you take the derivative of this expression with respect to u, you get h transpose. So it is like a row vector. Okay, so sometimes this confuses people. I mean, why does it matter if I get a row vector or a row vector or a column vector? Why should it matter? Well, if you continue doing this, if you like to continue multiplying stuff together, it is like shape really matters. But for now, I mean, in this case, it didn't matter because this is already a matrix and I can get this. But this is a vector and row vector and column vector kind of difference. So keep these in mind, and we are going to use this in taking the derivatives of, derivatives of this stuff, because I am going to take, this is what I'm going to do. This is AS, right? Okay. S is kind of our, well, I mean, from this one, there is one more layer, which is the logistic regression. Okay. And after that, we are putting all of them together into a single loss function. And I should take the derivative of that loss function with respect to x and b so that I can find them. But to make the things a little bit easier for us, I am going to take the derivative of derivative of s with respect to, I guess, I think this guy does it with respect to B. Let's see how it does. Let me see. Yeah, it does that. Yeah. So it takes the derivative of S with respect to B, which is important because B's are unknowns. So in this B, if I ignore this X, B's are unknowns. If I want to find the B's, which direction should I move in this world, and this is going to give me that one. But taking the derivative of S with respect to B is not easy because I need to apply this chain rule. So what am I going to do? Take, okay, sorry, this is what I was going to do. Take S with respect to H and take H with respect to B, right? Okay, but there is an F2, right? There is an F. Well, that's not going to be bad. Okay, that's what we are going to do now. Let's try to figure that out. Actually, we did this right before. We did this before, right? So if I take the
That will be U transfer.
yeah, that will be U, right? It will be U, because U transpose is going to be U again. But this one is going to be tricky. We are going to look at it in a few minutes. Okay. So this one, and I have this. H is FZ. Oh, you know what is doing? H depends on this one, and I am going to take the derivative of it. So I am going to take the derivative of S with respect to H, and take the derivative of H with respect to Z, and take the derivative of B with respect to X, because we missed that's function F. Okay, take the derivative of S with respect to H with respect to Z, and Z with respect to B. Okay, good. With the chain rule, let's look at this one. Okay, this one and that one is same thing. We already okay, this one is here and this one is there. Okay, remember these three rules we derived a few minutes ago, and we are going to apply them one by one. Okay, this one is S with respect to H. It is UT. I thought it would be
No, because we derived the U.
yeah.
So the transform.
It was just yeah. So this is the first rule, right? Okay, this one is HT, but I am doing it that way, the other way.
Yes.
Okay, this is UT. So I got this. Okay, and then now the second one, diagonal of F prime Z. So it is Z is a vector, F is a function. So it's going to be that one, diagonal of F prime Z. How about this one? Okay, this is already I. Okay, I put it in there together, all of them together, and this is what I get. Okay, it's a UT point product F prime Z. We don't have any dependencies on X. We have dependencies on U. Okay, so to guess the values of B, I should not consider anything about X's. X's are not related to me. That's what it says. Okay, and the nice thing is this. What did I do a few minutes ago? I calculated this partial derivative of S with respect to B. Now I'm going to calculate partial derivative of S with respect to W. Okay, this one. But the nice thing is that I already did this. Right? I already calculated that one. So I can keep it. It's like dynamic programming again. Of course it's not dynamic programming, but I can keep it and I can calculate that one and put it in there. Okay, put it in there. So these are the common stuff. These are the different stuff. I can put it in there. I will represent these common stuff with this sigma and sigma. And since this is identity, this will be the same. This will be different too. Okay. So at the end, this is what I am going to do. Take the derivatives that way and run this gradient descent function all over again. Get the new parameters for x and b and u2. Okay. Get the new values, run it again and run it again until I am tired. I cannot do this anymore. It has been 2 days. It is getting better, but I cannot do this anymore. Or until you don't see any improvements, you will say that this loss is not going anywhere. Okay, this loss is not going anywhere. I am fixed here, so I am going to stop here. That's what the gradient descent does. Okay, let me take some break. It is 15:24. Let's be here around 15:40. Then we will continue and we will try to connect it with the NLP problem again. Oh, I forgot about your attendance. Don't make me forget this one again. Okay.
Bu nasıl bir hava ya böyle? Sen bisikletle mi geleceksin? Tamam, bir zahmet yani bisikleti bırak Marmara'yla geri git. Marmara'yla içmelerden direkt otobüs evinin kapısına bırakıyor.
Üşümezsin ya. 2 dakika bisiklet alacağız. Bisiklet mi götürüyor?
Kardeşim, bu havada zaten sen fren basıp tutmuyor.
Hakikaten fren ben de diyorum niye bir şey
Şimdi sen E5'e çıkıyorsun bisikletle. Yokuşlara gideceğim.
Şişede gibi misin orada?
Arkadan bir giderse daha ileride yokuşlara ben hiç çıkarsın. Küçük kaza.
Ya bisiklet iyi. Niye? Çünkü evde olduğu için hareket yapıyorsun. Onlara bekliyorum. Ama işte soğuk hava.
Öyle mi düşünüyorsun?
Ya bence öyle. Açılıyorsun yani süper. Haftada bir iki olsa.
Ne yaptın? Bir fikir de olsa.
Ya nereden? Aslında çıkarsın.
Ben bir ara yogaya geçiyordum.
Okay. So derivative with respect to a matrix, that's what I mean. This is important, of course. Derivative with respect to the B, the biases, that's what we need to learn. Also, derivative with respect to this matrix is important too, and that's what we are going to look at. Okay, so that's what you are going to get actually, a matrix like that. Derivative with respect to 1, 1 and 1m, 1 and m. But each one requires some kind of a computation because between S and W there are many things going on, as we already know. Okay, so we know this already. Okay, Z is this much, and I came down to Z. Okay, I came down to Z. I already know that one, and I can add this multiplication and come back with the derivative with respect to W. Okay, these slides talk about the shapes of the derivatives and the matrices. It is important, but I don't have time to talk about because next week and the other week I have my last lectures. I don't want to spend that much time on it. Okay, so I'm going to skip the shapes of the matrices and why we are taking the transpose, and I'm going to continue with the rest. Okay, So that's the thing. Okay. Okay, so backpropagation. Backpropagation is this. It is nothing. It is nothing new. We already did that actually. When we have a function like this or a network structure like this, you get your x input. You multiply it with our weight matrix W. We add our bias and we feed it through this sigmoid function, and then I multiply the result with a U and etc. So sometimes I like to represent my networks using this notation, okay, graph notation, computational graph they call it. It would be easy for us to visualize what we are doing, and it would be easy for us to remember what we have done and what kind of things are common in this case. So again, this is not the complete network. After S, we need to calculate the sigmoid function or the softmax function, but we are going to stop at that point, and the rest of them is easy. We are going to look at this network as it is right here. Okay, so nice representation. In this case, edges pass along result of the operation. So this edge is W times X. Okay, this edge is Z, which is this one. This edge is X, H, as you know it. Okay, so the forward propagation is you give the input. I assume that I know W's and B's and U's. Okay, so these are the things that we don't know. This one, and this one. Let's say we know them. Perfectly, and given this X, I can calculate everything here. This is called forward propagation. Okay, this is called forward propagation. It is like this. Okay, if somebody gives me this X, I know F, I can find, okay, this position. So this is F of X, right? So this is forward propagation. Okay, so somebody is giving me this X, I can calculate everything there. But the thing is that at the beginning, we don't know W, B, or U. So we start our training phase by assigning random numbers to these unknown weights, W, B, and U. Okay, just random weights. And then by using this, by calculating this gradients of S with respect to X, okay, sorry, gradient of S with respect to B, with respect to U, with respect to W. Now I can calculate which way to move in terms of these parameters in my space. Okay, so that's going to be the back propagation. So forward propagation is just feeding that information and getting results. Okay, back propagation is through the gradients. Okay, you are through the gradients, you are feeding the gradients backwards so that I can calculate this one, I can calculate this one, and I can calculate this one. Once I calculate them, you know the formula. The formula is the gradient of this F of sigma star. Okay, so sigma minus sigma star. Thank you. Okay, so that's the rule, and it is easy to use these kind of computational graphs to show this procedure stuff. So I have a single node here. Z is the input, H is the output. Downstream gradient, upstream gradient. Remember, I get something from here. Okay, when I multiply this one, okay, with whatever I have calculated, okay, it becomes the chain rule. That's what I'm trying to achieve. So this is the downstairs, okay, downstream gradient, upstream gradient. Okay, if H is Fz. So what I'm gonna do with the chain rule? This is my local stuff, okay? Derivative of S with respect to H, derivative of H with respect to Z. Then, if you multiply this one, these two together, I would get derivative of S with respect to Z, right? So it's going this way, back propagation. This is forward propagation. Okay, that's like I said. Good. So once you get this, okay, by the way, this graph is a very simple graph. Usually for our networks, we have hundreds of nodes like that. Okay, by looking at this kind of a graph, only you can manage to find these derivatives and the correct ones. And by looking at this graph, I can do it in an efficient way. Okay. So we talked about those. How about these kind of weird cases? It can happen, right? Z is W comes from here, X comes from there, and Z is the multiplication of these two. Okay? We have never seen such things before.
Here we have WX, but we just forwent the
Yeah. Yeah. Well, yeah, that's true. That's true. I was confused about the other thing. Okay. So this is just a standard thing. So I looked at this one. I looked at this one in a few minutes ago using the standard chain rule. How about this position now, right? W comes here, X comes there, and how does the same thing here, right? Put it the plus. How does the back propagation works in this case? Okay. So I get partial derivative of S with respect to Z. My local derivative is this. I just multiply these two together and I get this one, right? And I multiply these two together, I get this one. Okay? So if I have plus here, if I have plus there, like that one, and I'm going to do that the other. I mean, instead of a plus multiplication, there will be a plus. This slide has a very nice example here. This example says that, let's say I have a network like this. Well, the nice thing is, doesn't matter if these are scalars or the vectors or the matrices, it's going to work the same way. Okay, so forward pass is easy to calculate. X, Y, Z, just add them together, choose the maximum of it, and then multiply it. Okay, so this is f x, y, z. Now I am going to calculate. Derivative of f with respect to x, y, and z. Okay, x, y, and z. So f is here. They are way back here. I am going to calculate derivative of f with respect to x, y, z. It is not like anymore like at every step there is a function. I am doing it. At every step, this is like there is a function, but in this case there's plus, then there is this maximum. That's what I'm going to do now. And this guy tells me that calculate this, okay, this forward probe and backward probe for this position x1, y2, and z0. Okay. So if I put x1, y2, and z0, f becomes 6. This is the forward propagation, no problem. Okay, no problem. How about this backward propagation? Let's look at that one. Okay, so for this plus, okay, calculation of a, x plus y. If I take derivative of a with respect to x, okay, derivative of a with respect to x is going to be 1 because, I mean, and the same thing is for y. It's going to be 1. Okay, 1 and 1. And that's, I am done here. Let's look at this max stuff. Okay, if I take the derivative of max yz with respect to y, it's going to be 1 if y is greater than z. Okay, and it's going to be okay, it's going to be 1 if y is greater than z. Derivative of b with respect to z is going to be 1 if z is greater than max y z, maximum of y and z, right? Yeah. Oh, okay. So it's going to be 1 because in that case derivative of b with respect to y is going to be derivative of y is going to be 1, and this is 1 for the z, and I know that y is 2 and z is 0. In this case, derivative of b with respect to y is going to be 1, and derivative of b with respect to z is going to be 0 because I know these values. Okay, so I have calculated them. This is good. And when I come to this one, derivative of f with respect to a is going to be, with respect to a is going to be b, which is 2, which is 2 that it comes here, right? And the other way, the derivative of f with respect to b is going to be a, which is going to be 3 here. Okay, so by the chain rule, I know what to do. Okay, if I come back, I can calculate this one, and this one, and that one. And let's do it. So derivative of f with respect to f is 1. And then I'm going to do derivative of f with respect to a. I think it's going to be put in here. So it is going to be 1 times 2. 1 is this. 1 is already found. 1 comes here. Okay, 1 is this, and the same 1 is going to be there. Okay, and 2 is derivative of f with respect to a, so it is 2 and 2, 2 and 3. Okay, so I am back propagating, I am back propagating my derivatives from the loss function back to the originals, back to the input, and doing the same thing for this max. Okay, it is going to be 0 times 1 for this part, 3 times 1 for this part, 3 times 0 for this part. Okay, and if I go up, I will do the same calculation for the x. Okay, so this is derivative of s with respect to z, derivative of s with respect to y, and derivative of x with respect to x. Okay, these are the calculations, and this one is total of 5, 2, and 0. What does it say? It says that to minimize the value of the loss, doesn't matter where you move z, f is not going to be changed. If I increase y a little bit, okay, f is going to change, right? F is going to increase. And if I increase the value of x, f is going to increase too, right? So if I like to minimize this, it makes sense to don't play with z at all. Okay, keep it same. Okay, lower y and lower x. That's what it says. Okay, so if I am going to optimized with respect to XYZ values. Okay, so this is I mean, three things can happen. Either it goes in and goes out, or there is a branching. Okay, and when you branch it back, you add them together, like that one. Okay, already we looked at those, and this plus and the plus and what the plus and maximum does, okay, plus distributes the stuff, okay, it just distributes the upstream gradient, max routes the between them, so it just this 3 one of them, 2 is one of them. Okay, so what we did before was this. Coming back here, derivative of s with respect to b, we already calculated that one. Okay, so if we are going to calculate this one, it doesn't make any sense to calculate these altogether again. That would be very, very inefficient. So that's the correct way is to use compute all the gradients once. You start from here, you calculate this part first. Whatever you calculated in a common way, calculate and come back all the way down to the last unknown place.
Question, don't we back propagate to u?
What's that?
Well, don't we back propagate to u?
What does it propagate to you?
U, the first one, the one to the right. Yeah, don't we back propagate to it?
F, S, yes. I take the derivative of S with respect to u.
Yeah.
That was a simple case.
Okay.
But for the one, I mean, it starts with S with respect to S.
I understand that.
So I mean, I'm trying to. I think I'm trying to maybe understand your question. So for that one, after calculating that one, we didn't use anything out of this calculation. But out of this calculation, I have to use all that stuff to calculate this one.
My question is, for the next round,
Yeah.
we will be changing W and B, getting from depending on the results from the ds over dB and ds over dW, right?
Sure, our parameter set is W, B, and U. Okay.
So we also change U, right?
Sure, yeah. But they are all our parameters, yes. They are all our parameters. Remember, I mean, we don't know the values of this U, B, and W. At every step, at every gradient descent step, we change their values and we push them towards the better place. At least that's at least what we think about the better place. It may not be a better place. After testing it, we are going to see it. Okay. So this is the rule. Okay. Back propagation in general computation graph. Forward propagation is simple. You put your inputs. Okay. You assume there is the randomly distributed, normally distributed weights at the beginning. Okay. You follow all those black lines, and you found your scalar output z. Okay. And then you take the derivative of z with respect to all of the unknowns. That's what we're trying to do. So you start with initialize the output gradient to 1, and you back propagate. Okay. And once you back propagate, you are going to find all the derivatives. Okay. Remember, we are trying to find this one, derivative of this loss function with respect to all the parameters. Once I have found this, I multiply it with an alpha and subtract it from the old parameters.
Oh, so the parameters here are W. No.
Okay. Are there any other moments? Yeah. That's, I mean, maybe it was my fault when I say this is fx. X here is the not known. Okay. Maybe it's better to, okay, it's better to say it's not maybe f theta x. X is known, but thetas are not known. Okay, so we are trying to find the parameters of a function, but these are kind of meta parameters. Function f is going to be guessing if this car is going to be sold or not, okay, but we don't know the parameters of that function. Okay, so this whole network unknowns becomes your parameters, and with this step I keep changing those parameters. At the beginning I initialize those parameters to random values, and random values doesn't make much sense. Okay, they produce something. And let's go back to, in fact, let's go back to this one. This one, this one, this one, yeah, this one. So at the beginning, let me shuffle this, where is this? Yeah, I shuffled it. Okay, and discretize output. Okay, so all these numbers are, these weights are all random numbers, including the biases, and this is what is giving me. So it says that my loss is 0.5. Almost half of them are incorrect. That's why? Because it is trying to say that everybody is all blue. So half of all the blues are correct, all the yellows are bad, so 50% success rate. If I go one more on this, let's choose one better example. This one is better, yeah. So if I go one step means that, okay, one step means that put a few 10 samples, that's the batch sizes, okay. Put 10 samples from the training case, okay, forward propagate it, and get the results and backward propagate it and update your values. So one of them did that, and as you have seen, now I have a little bit better, I think it's a little bit better configuration here. Just one, this is just one movement of the parameters. For we don't use all the batch, we don't use all the training data for a single step, because that would be too much and that's not good for the gradient descent. Let's make this 29, okay. Let's run this for the 29 of them. No changes. Yeah, now it all became yellow. Let's run this a little bit faster. It's going to take a while, I guess. By the way, this learning rate is the alpha, 0.03. This is alpha, okay. And see, my classification front is coming from that, and my values are still bad, but it might find something. How did we solve this a few minutes ago? It was very nice. One epoch means that I have put all the data once to the forward propagation, and I have backward propagated all that information. Now I am going to do it with the same data over again, second epoch. And my numbers are not dropping much, but they are dropping. They are doing something, okay. Very slow progress. This gradient descent always go very, very fast.
If we increase the learning rate, would it drop faster?
If I increase the learning rate, what was the problem with the increasing the learning rate? It can jump around a lot, like crazy, forward and backward. So sometimes by luck, it just lands into a nice place, and after that, yeah, so it is something, right? I think this is doing, yeah, losses matter, right? So it is rotating. It behaves like it's doing something intelligent, but all it does is, okay, it is just following the gradients. Gradients of these. How many parameters do I have? 1, 2, 3 here, 3, 4, 5, 5, 10, then 10 there, okay, 10, then 5, 5, 5, 5 there, 20, 30, and 35 parameters total of. So this is a search in a 35-dimensional space, and it found it, I guess. Yeah. So loss is getting better. That was the graphics of the loss. And it looks like I cannot do much about these, and I cannot do much about that one, because they are within each other. That's the noisy points. That's the effect of life. Maybe if I can do better, maybe I can take these in. But it looks like it's going to be around there. It is better than 0.1 loss rate. Okay. So after trying each point just 2 times, I almost get the idea. For the large data sets where you have billions of images, okay, we are talking about images, billions of images like the MS COCO data set, sometimes you have to do this thousands of times, this epochs. And each epoch is going to take 1 or 2 hours. So you have to do this parallel. Not many companies can do that kind of an optimization. So if you have the data, if you design your network in a nice way, then you should be fine. Okay, so let's stop this. Let's stop this and let's increase the learning rate by 3 times. Start from the beginning. It is not doing much.
Decrease it by 3 times?
No. It is 0, 0. It started from 1.0 to.
The learning rate wasn't at 0.03?
Ah, yeah, okay. So I went the wrong way. Let's stop this. Let's start with a higher learning rate. So it immediately caught something. It is moving much faster. So it looks like maybe this kind of a learning rate is a better for this kind of a network. So it is getting back. Oh, okay. So it did something crazy there. Well, not bad. Much faster. So even without doing the even without doing a single epoch, it did nice. Let's do it with a 1, or let's make it completely crazy. Okay. See this one? Loss is like, how come a loss can be
1.
well, more than 1? See what is doing? See all these numbers?
Seems like random.
Well, because it is just, well, not bad. Okay, sometimes we do this. After doing that, okay, we say that, okay, now you are a grown man, okay, do this. Okay. So it's going to be much more careful with the data. I think this is too much, like that.
Is it doing anything?
It's doing something, yes. These are stuff. So it looks like it is stuck with a local minimum. So maybe it is stuck there.
Yeah.
I don't know. So make it a little bit larger. I think it hits a local minima. It is not moving anywhere around. So it looks like, it looks like this gradient descent is no known thing. It's just a heuristic. It doesn't guarantee that you are going to find the optimal values. It doesn't guarantee that you are going to converge. Sometimes it doesn't. So all you do is you just change your learning rate, this step size. Also, what else can you play with? You can play with your network structure, add more nodes or remove nodes, change your activation function from sigmoid to some others. Those are the things that you can play with. But basically, this is what you are going to do. And let's go back to this. Let me finish this up. With the PyTorch or the TensorFlow, they give you this kind of stuff. You say that, what is your network? This is my network, okay? Forward propagation is easy. For the backward propagation, give me how am I going to calculate your, how am I going to calculate your backward stuff, these derivatives, okay? So you give your derivatives there, okay? Multiply my y with dz, okay? I'm going to get the dz, etc. for this kind of stuff. And these are standard, and you can add them together. Even you don't have to code this much yourself. So as the final thought, for the neural networks, this is what's happening for the back propagation starting from 1984. One way or the other, people are using back propagation to train neural networks even today. Doesn't matter what kind of data you have, what kind of computers you have. We do the back propagation. So recursively start doing the same thing. Apply the chain rule along the computation path. And downstream gradient is upstream gradient times the local gradient. That's what we are doing. For the forward path, we put it in place and you will get the results. For the backward paths, we apply the chain rule. Okay? So that's what we have been doing. And for the last 10 years maybe, we have enough number of CPU cores or the GPU cores and the memory and the training set, so we can do this kind of stuff on real world data. And it works very well for the images. It works very well for the computers, for the NLP, and that's the basic thing about it. Okay. Modern deep learning frameworks such as TensorFlow or PyTorch, they calculate the gradients for you. So that's the question. Why are we talking about these gradients then? I mean, why didn't you just show us the functions that calculate these gradients for you? Well, I mean, it is always important to know what's going on. Okay. You need to know how the things, work. It's like taking a compiler class or trying to understand a programming language, how it works. So it is important to know how these stuff work. So you know how it works. Next lecture and the other lecture, I will make 2 more lectures. Next week is the last week of the semester. The other week I am going to make 1 more lecture, and then maybe we should reserve some time for the graduate students to do their presentations, and I'm going to talk about it maybe next week. We'll make that plan, and I'm going to show you very simple translation system based on the neural networks from English to Turkish, Turkish to French or whatever. Okay, and after that will be it, I guess. Okay. Any questions? Okay, I'll see you next week then.